The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So today we're going to talk about bit hacking, okay, which is a topic that has a long, long history in computer science. We'll only cover on a few of the a few techniques. So let's just get going, okay? So I want to swap two integers. Okay? So I think most of you would know how to write a program to swap two integers, and it would look something like this. And mostly this is pseudocode. I'm not going to be doing declarations of types and writing full code in order to make sure things get on slides and so forth. So what do? You assign a temporary to the value of x. You then let x take the value of y, and then you let y take the value of the temporary. Okay, what could be simpler? Okay, well, how about doing it without a temporary? So how do you swap two numbers without a temporary? So here's one way. Okay. So what's going on there? So the caret is an XOR, exclusive OR. Okay? So here's what's going on. So here, let's do an example first. Okay, so I have x and y. I then let x be the XOR of x and y. So as you see, that's first bit is the XOR of 1 and 0. The second bit is the XOR of 0 and 0, which is 0. The third bit is the XOR of 1 and 1, that's 0, and so forth throughout the bits. Okay? So then I let y be the XOR of x and y. And then finally I let x be the XOR of x and y again. And now if you notice, that number is the same as that number, and that number is the same as that number. Okay? Magic. We're going to see a lot of magic today, actually. Okay? We're going to see a lot of magic today. Okay? No temporary. Okay, why does this work? So the reason this works as a great property of XOR is that it's its own inverse. Okay? So if you take x exclusive OR y, and you exclusive OR that with y, you get x. If you were to exclusive OR that with x, you would get y. So that first step is basically putting in here the XOR of x and y, so that when you end up on the next step computing the XOR of y and this, you get x. So now you've got x here, and you've got x, the original x. You've now got the original x XORed with y here. So to get back the value of y, you just XOR out the x. And so it swaps them. Okay, whose brain hurts? Okay. Okay, you can study these later on. But a pretty neat trick. Pretty neat trick. Does it perform well? Turns out, not really. And the other way is actually a better way of doing it generally, with most compilers and architectures. And the reason is because the other way of doing it, you can actually essentially pull two things out of memory, one into a temporary one, and then stick them back like this. That's what the compiler ends up doing. Okay, whereas this one, it has to wait for each step. And so you don't get to exploit instruction-level parallelism. So remember from last time, instruction-level parallelism is the fact that a processor can issue more than one instruction at a given step. And here, this sequence of operations, each step has to wait until the previous one is computed before it can execute. So you get no instruction parallelism in this. So it's not particularly high performing, but there are other places where we'll use this kind of property. Okay, but it's a neat bit hack. Swap two things without using a temporary. Okay, now here's a real bit hack and a real useful one. Finding the minimum of two integers x and y. Gee whiz, let me just call a subroutine or something. Okay? So you might be tempted to write something like this. If x is less than y, then the result is x. Otherwise, the result is y. Seems pretty straightforward. Or if you know a little bit more C, you can write it as, with this sort of cryptic, if x is less than y, then x else y. Okay, so those are two equivalent C ways of doing things. Okay, so what's wrong with that? Well, nothing if you don't mind slow code. Okay? In fact, for something like this, the compiler actually will optimize it to deal with it. But let me just point out a couple things. First of all, there's the processor has within it a branch prediction unit. Okay? Whenever it comes to a branch, it guesses which way the branch is going to go and proceeds to speculatively execute along that path. If it turns out to be wrong, it says, whoa, hold your horses. Got to go that way. Okay? To do that, it empties the processor pipeline, and that takes, on the machines we're using, around 16 cycles. Okay? So you don't want to have branches that are mispredicted. And in particular, what you want to look for in conditional instructions is whether they're predictable. Okay? So something that's almost all the time branching the same way, that's a predictable branch. The hardware is very smart about figuring out how to predict that and will make the right prediction, and you won't pay any performance penalty. Okay? But if you have something where you don't know which way it goes, so in a code like this, okay, the compiler, the architecture isn't going to know if you just throw at it various pairs of x and y. It has no way, it's a 50-50 guess whether it guesses right. So half the time, it's going to predict the wrong thing. Okay? So compiler might be smart enough, but maybe not, but you can be sure. Okay? And here's a way of being sure. You write this code. Okay? What is going on there? Okay? So here we go. We're taking x less than y and taking a minus sign. Yike. What's that do? Well, C represents the Booleans true and false with the integers 1 and 0 respectively. So if you execute the operator x less than y as opposed to doing a conditional based on x less than y, it returns either a 0 or a 1, depending upon whether it was successful. So when you take the negation of that, this is either 0 or 1. It's either going to be 0 or minus 1. And what is minus 1 in 2's complement arithmetic? It's a word filled all with 1s. So you either get a word all filled with zeros, okay, or you get a word all filled with 1. So if x is less than y, you get a word all filled with 1s. Okay? So then what are you doing? You're doing x XOR y, and you're ANDing it with all 1s. Well, that's a no-op, to AND it with all 1s. Right? To mask something, if I do an AND of anything with 1, I get whatever the thing is. So this expression ends up evaluating to just x XOR y. Great. Then what? I take y here, and I XOR it. I get back x, because of that inverse property of XOR. Okay? So if x is less than y, then r gets the value of x. Okay, if this is not, if x is greater than or equal to y, then this expression evaluates to 0. And a word of zeros ANDed with X or Y gives you a word of zeros, because 0 is an annihilator for AND. Okay, it always, whatever you AND with 0, doesn't matter what it is, you get 0. So therefore, this just becomes R equals Y. Did I do that right? Because Y XOR 0 is Y. Okay? So pretty clever. Is this really better? Seems like an awful lot of operations. Well, the answer is yes, it is, because all of this goes on within the processing unit, okay, rather than with anything having to do with memory. Okay, it gets the values for X and Y to begin with, and then it's all instructions within the processing unit. Those typically take one cycle. And if there's any parallelism in it, the parallelism will give you, it'll be able to execute even more than one operation per cycle. Okay, in fact, the machines we're using are 6 issue. Can run 6 operations simultaneously. Okay, each taking a cycle. Okay, so the difference between that and going out to memory is really quite considerable. So everybody follow that? Okay? Pretty cute trick, how to make it go fast. Yes, question?
Since the expression is tested, doesn't it have to be wait for like the compute the inner expression before you can compute it?
No, there's no, this is a comparison. This is operated like a, so there's no compare instruction there. It's a CPU operation. Okay, it's an arithmetic and logical operation of the CPU that it can do in one cycle, is to compare. To change, the normal thing that you're trying to do if you have an if is you're trying to change the program counter. And that's what's costly, not the actual doing the test of the branch, test of the of whether X is less than Y. Okay?
So you have to wait for that to finish before you can do the negation?
Yes, you do. So that's 1 cycle, 2 cycles. We can add it up here. 3 cycles. This can be going on in parallel, so it's really only 2 cycles. Okay? Total. 3 cycles, 4 cycles. So in 4 cycles, you can get the minimum done. That's actually the L1 cache in the architecture we're using costs you 4 cycles to fetch something if you get a cache hit in the L1 cache. That's the cheapest memory operation you can do is 4 cycles. This computed the whole minimum in 4 cycles. Okay? Good. Okay. Here's another one, modular addition. So sometimes you want to, know something that the compiler doesn't know. Like suppose that you know that X is between 0 and some value n, and Y is between some 0 and some value n, and you want to compute their sum. So what you know is that the sum is going to be less than what? 2n. Okay? So normally a modular operation is very expensive because it involves a divide. Now multiply is normally more expensive than an ordinary ALU operation that's just a bitwise operation, like addition or XORing bitwise XORs or comparison or what have you. Those are very cheap one-cycle operations. Multiply is usually a many-cycle operation. Okay? Divide is often implemented by doing repeated multiplies using any of a variety of techniques, including Newton techniques. Sometimes there is a divider or a divide step, but divide is generally, in any case, more expensive, even though it's doing operations all within the processor. So if you actually compute mod using your percent thing, this is actually can be quite expensive, unless you're dividing by a power of 2. If you mod a power of 2, that's easy because the processor, if it knows it's a power of 2, if the compiler knows it's a power of 2, it'll just do a masking operation on the low order bits, okay, to give you whatever the remainder is, mod 2 to the n. Okay? But if you're not in that situation, n may not be a power of 2, you still want to do something mod n, there still are some tricks you can play. But the compiler won't, this is one the compiler generally won't play for you, because the compiler won't know that these are preconditions in your code. Okay? By the way, one of the most common things is just doing x plus 1 mod n. Okay? Very, very common thing to be doing, x plus 1 mod n. Okay? Where you're wrapping around in some index space. Okay. Here's another way you could do it. So that's divide is expensive. Here you could just say z equals x plus y. And then if z is less than n, give z otherwise z minus n. Okay? And the problem with this is that it's got an unpredictable branch. To execute this code, I could have written it out with an if statement. It's got to change the program counter to execute either this or this. Okay? So not very fast, because you have an unpredictable branch, and we already talked about that has to empty the pipeline if it's wrong in the guess. Okay? So here's a way of doing it which doesn't have an explicit branch. Okay? So we compute x plus y, and now what we do is we look at whether z is greater than or equal to n. Okay? And if it is, we're basically going to take the negation, so that if it's greater than or equal to n, the negation here is all 1s. Once again, is minus 1. And so this becomes n ANDed with minus 1. Okay, that gives me n. And so then I'll take z minus n. That's what I want. However, if this is z is less than n, okay, then this will evaluate to 0. Minus 0 is 0, and n and 0 is 0. And so I'll end up just getting the x plus y. So it's basically the same trick with a couple of twiddles on the minimum that we saw on the previous FOIL. Okay? Who's having fun? Okay? Good. Okay, yeah, these are, as I said, we're going to see lots of tricks, magic tricks even. Okay? Okay. Round up to a power of 2. This is a common thing that you want to do here. This is, for example, goes on in memory allocators, which we'll talk about later in the course. So in a memory allocator, somebody asks for a hunk of storage of size 19. Most memory allocators want to give out chunks that are powers of 2 for reasons that we'll discover later. So you want to round up to the next higher power of 2. Okay? So how do you do that? So here's an example. Okay? So what I do is I decrement n, and then I update n, ORing it with the left shift of n. And then ORing that with the right shift of n by 1, then the right shift of n by 2, et cetera, et cetera, et cetera. Okay, so here's an example. Okay? So here's my original number. And what I want is to round it up to the next power of 2. This is what I'm going to end up in the end. See, I've got the next higher power of 2. Just 1 bit is on if I've rounded up to the next higher power of 2. Okay? So what did I do? I basically decrement, okay? And then I take this word and I shift it by 1 to the right and OR it in. Okay? And then I shift it by 2 and OR it in. And then I shift it by 4 and OR it in. Okay? And then, in fact, I shift it by 8 and OR it in, and I didn't do that. And since this isn't a 64-bit word, I skipped the last 2 instructions. Okay? So what's going on when I'm shifting and ORing it in by 1, by 2, by 4? What's happening? Yeah?
This way there's no number of ones starting from the 1.
Yeah, basically from the most significant bit, if you look at what's happening with the most significant bit, okay, you're shifting it by 1, then you're shifting it by 2, you're flooding the low order bits with 1s. And because it's an OR, As soon as something gets set to 1, it stays a 1. So it doesn't matter what's actually happening in the low order bits. The only bit that we care about is this bit. And it basically floods all of the other bits with 1. Okay? And then once I've flooded them all with 1, I increment, and that gives me a carry out to this position and gives me the next higher power. So why did I decrement here and then increment there? What's the decrement for? Yeah.
So that you can flow with 1, so that because you want to get your result back, so you want to add 1 up to get a power of 2 to decrement first.
Well, why did I decrement first?
I mean, so if you were not to decrement, you would just flood everything at once. And then
Well, here, if I didn't decrement right here, I would have gotten the same result. Yeah, you already have a power of 2. If I already have a power of 2 and I flood the low order bits, okay, then I increment, I'll get the next higher power of 2. So by subtracting 1, I make sure that I'm handling that base case when n is a power of 2. Yeah?
Does the plus and the minus operator before to save cycles?
Actually, the compiler is not going to care in this case. Okay, but it does make sure that it doesn't bother to try to return keep around the old value. But it's smart enough to, to not worry about that. So, yeah, I mean, some people like postfix decrementing, and some people like prefix decrementing, and it doesn't matter in most cases. But sometimes doing it after, there are situations where doing it post-decrementing costs you a cycle. Okay? So everybody got the idea here? So basically round up to a next power of 2. Okay. How about computing a mask of the least significant 1 in a word? So I want a mask which is the power of 2, the word that's all zeros except for a 1 in the least significant 1 bit. Any ideas how to do that? Okay, this is a classic trick. Everybody should know this trick. Okay? You take x and you AND it with its 2's complement. Okay? Take x and AND it with its 2's complement. Why does that work? So here's x, some value here. The 2's complement is it's the 1's complement plus 1. Right, if you remember. So 1's complement just means I complement every bit. The 2's complement is I complement every bit and add 1. So when I complement every bit and add 1, basically these, I go all the way to the least significant bit, and then I get zeros after it. So right up to there I get, it's 1's complement, and then it's basically, would have been 0, 1, 1, 1, 1, 1, plus 1, the carry pulls you back up to there. Okay? And so then when you AND them together, oh, look at that. There's our least significant bit sitting there. Okay? Okay, pretty good one. Okay? So how do you find an index of the bit? So by an index, I mean this is bit 0, 1, 2, 3, 4. Well, it turns out these days many machines have a special instruction to do that. And so if you look around and you find the right library that calls that instruction, you can use that instruction pretty cheaply. But there still are a lot of machines, especially things like mobile machines, et cetera, where they have a depleted instruction set, where they have no instruction to convert from a power of 2 to essentially its log base 2. So LG is the notation for log base 2. Okay? So how do you go about doing that? Okay? So what we're going to do is do some magic to motivate the solution to this. Okay? So one way to do it is to use the ESP instruction. Are people familiar with the ESP instruction? Okay. What's that? The stack pointer? No, that's BSP on some things. Or E, yeah, right. So in the extended instruction set, there, yeah, okay. Yeah, so the ESP instruction, extrasensory perception. Okay? And we have today the tremendous magician, tautology, okay, who is going to demonstrate the theory behind finding the index of the bit. Okay? So please give a warm hand for tautology. Where's the...
Can everyone hear me?
We need the handheld. We have the hand. Oh, you ran past the handheld.
Well, that was a little less. Oh, well.
We're in the card tricks.
How about now? Can everyone hear me? Ooh, I'm on a mic. Crazy. So, as my good friend Professor Leiserson has mentioned, I am the amazing tautology, and today I'm going to show you an amazing card trick, which will baffle your minds for approximately 5 minutes until he shows you the next slide. All right, but to do this, I will need 5 volunteers from the audience.
Who can follow instructions.
Yes.
So who would like to volunteer to participate in
Raise your hands high.
real magic? Here we go. Okay, 1, 2, 3, 4. Only 4. Okay,
Come
we
on,
need one
we
more.
can get one more
so
person,
come on
right?
up and line up along the front here. We need one more volunteer. One more volunteer. You get extra points. Remember, participation is part of your grade. Okay? Okay, I'm going to cold call. Okay. Yeah. Here we go.
All right, excellent.
Yep, anywhere.
Please cut this
In line.
deck. Cut it. Yes.
First, you got to show its random deck.
All right, I will first show you that it's a random deck. You mind holding this? Yeah, sure.
See? It's all mixed up.
See,
Can't see it close.
Okay? So it's only 32 cards. It's only 32 cards. So we pulled out some of the other cards, but they're in a pretty random order there. So we want to give everybody a chance to shuffle the deck here by doing a cut.
yes.
Good. Pin, cut pin to win, yes. Excellent.
Take the top.
Look at it.
Yes, look at it. Okay, but don't show it to tautology. Okay, now don't show it to him. So why don't you go around the back so that the class can see the cards?
Wrong side of the cards.
No, then they'll turn the cards around to let the class see. Okay? So hide your cards while he runs around behind. Okay, and then turn them around so that the class can see what the cards are.
All right, are you guys ready to turn around?
Okay.
Cool. Excellent.
I'm not going to look at them either. There are no dupes. This is all done by ESP.
All right. Now,
Why don't you
I'm
come over
going-
here where you can see the class?
Hello, everybody. I am going to tell you what is on those 5 cards, which I have not seen. Behold, I have not seen them. Okay. Are you guys ready? Here I go.
Okay, now you got to think about them. You got to think hard about what your card is. If you're not sure, you can check, but you got to think real hard about what your card is.
Okay.
Are you guys thinking hard? I think you need some technological assistance.
I could use some technological assistance.
There we go. Okay. This is our brain amplifier, okay? It amplifies the brain waves coming from you to him. Okay,
All right.
give it a go.
Hang on. Is this thing on? There we go. Now it's on. Okay, here I go. All right, guys, I'm having kind of an off day. So I'm going to need a little bit of help. Can you guys just raise your hand if you're holding a red card? All right. So that's a red.
Red, red, black, red.
Okay.
They did it right, right? We got a whole bunch of...
All right. Now let me give this a shot. So red, black, red, red, red.
No, red, red, red. Oh, okay. You do it. Yeah.
Yes.
Yes, okay, you do it. Do it. You do it your way.
Now I might be wrong, but I think, am I seeing a diamond with a 7 on it? Is that what I'm seeing?
Oh, how
Excellent.
impressive is that?
Okay, 1 down, 4 to go. Let's see. What else am I seeing? Believe I am seeing, you're gonna have to think about this card pretty hard. I'm having an off day. So, I think I'm seeing a spade with a 6. Thank you for your honesty. Thank you. It does mean a lot to me, this class. All right. So, seeing a, let's see here. Now, what am I seeing now? What could this be? It's some kind of a heart. I think, just maybe, it has the value of 5.
Oh, 3 in a row. I don't think he's doing this at random. There must be ESP at work here.
Clearly, yes. It's all the hat, to be honest. It's all the technology. Just the latest technology. All right. So.
It gets harder as we go.
It does get harder as we go. But what is this? I think, no, it can't be. Can it be? The 3 of hearts?
Oh!
It's the 3 of hearts. My old nemesis, the 3 of hearts. Okay, just one more card. Did you just swap cards? I think I just watched you swap cards. Well, I'm just going for in the set, not
And they
necessarily
did it
in
without a
order,
temporary
you know.
notice. They must have XOR'd them together or something.
So the last card, which may or may not be in the last person's hands. Let me see if I can see it. Oh, what could it be? What could it be? What could it be? No. No. No, anything. Not that. Not the 6 of diamonds. It's not the 6 of diamonds.
All
there's the
right,
6 of diamonds.
5 out of 5. Thank you, thank you.
Thank you.
Okay, you guys, go back to your seats. Okay. So that's a pretty easy trick, right?
Yeah, pretty easy.
So how does it work? What's the basic idea behind it? What's the basic idea behind it? So, key thing is that how many bits of information did he get? 5 bits of information, and there were how many cards in the deck? 32. So the pattern of the 5 bits, okay, of which cards were read, let him know where in the cyclic sequence of cards he was, right? Because the cards really weren't random, they just looked random. Okay? And so 5 bits is enough, but that means that every sequence of 5 cards in that deck, as you rotate it around, has to have a different bit pattern. Okay? So does anybody know a name for that property? A sequence that has, a circular sequence that has that property? I'm sorry? The property is that if you, well, let's see, maybe I have it up here. Okay. So, yeah, here's our magic code, which is going to compute the log of x. And it's using what's called a Bruijn sequence. So let's come back to the magic trick in a minute. And let's look to see how we compute this, and then we'll understand how both work. Okay? So this is basically, there's a magic number here, okay, called de Bruijn. Okay, de Bruijn was a Dutch mathematician. Okay? And then there's this funny table, conversion table, and to find the log of x, where x is a power of 2, I multiply x by this magic number here, right shift at 58 places. This is keeping how many bits after the multiply here? 6 bits, because it's a 64-bit word. Okay? And then looking it up in this table. Okay? So let's take a look at what's going on there. So a de Bruijn sequence S of length 2 to the k is a cyclic 0-1 sequence such that each of the 2 to the k 0-1 strings of length k occurs exactly once as a substring of S. That's a mouthful. Let's do an example. Okay, smaller. So for example, k equals 3. So here's a sequence 0, 0, 0, 1, 1, 1, 0, 1, base 2. If I look at the first 3 bits, it's 0, 0, 0. The second 3 bits is 0, 0, 1. And notice that as I go through here, every sequence, and these are wrapping around the end, it's taking the last bit and then the first 2 of the end, every one of these gives you an index of every different bit pattern of length 3. So these came up because people played with those, those keypads where you have to enter a combination, right? And if you have a keypad and you want to enter a combination, let's say the keypad has only 2 numbers on it, 0 and 1. Okay, and you have to hit the right sequence of k numbers. So the naive way of doing it would be to say, well, let's try 0, 0, 0, 0, 0, 0, 0. Then let's try 0, 0, 0, 0, 0, 0, 1. Then 0, 0, 0, 0, 0, 0, 1, 0. So what that'll do is you'll have to go through 2 to the k numbers, each of which is k bits long, for k times 2 to the k punches in order to be sure that you've hit every number, okay, to open the lock. Okay? The de Bruijn sequence takes it from k times 2 to the k down to 2 to the k. Still exponential in k, but there's no k at the front, because it's making it so that each sequence that you have nests into the previous one. Okay? And that's basically what's going on here. Every sequence of length 3 exists, okay, in the de Bruijn sequence. And so this one here is a de Bruijn sequence of length 64, as it turns out. Okay? And what we had in the magic trick was a de Bruijn sequence of length 32. So when you cut the cards and you looked at the first 5 cards, that was a unique pattern of reds and blacks. Told you where you were in the rotation of the sequence. Okay? And then there's a little bit of cleverness to how it is that you translate that into cards, because remembering 32 cards and what their sequence was and so forth, that's pretty hard. Okay? But it turns out you can just do an encoding of the 5 bits. 2 of the bits encode the color, the suit. So the high order bit encodes the suit. The 2 bits encode the suit. Okay? And then the last 3 bits tell what the number is. Okay, 1 through 8. Okay? So that's, how that worked. It wasn't really magic after all. Who's surprised? Okay? So how can we use this in this particular code? So for this, basically the convert table does the following. It says, well, if you've got 0, the offset, the shift of this amount here is 0. And if you've got 1, then the shift is 1. And if you have a 6, where's 6 in here? Here it is. Wait a second. If I have a 2 here, then that's going to be that I'm 6. So this is inverting, this table is inverting this number. Does people see the relationship there between the table and, so if I know what the pattern is, I can do a lookup and tell how much did I shift by. Okay, if I am shifting by a given amount there, or circularly shifting. So here's the way that code works. It takes, let's say we've got a number like 2 to the 4th that I'm trying to figure out what the exponent is. Okay, it's always a power of 2. Okay, so I'm looking at 2 to the 4th, and I want to extract 4. But all I have is the mask that's 16, which has the 1 bit on. So what I do is I multiply this number, okay, the de Bruijn sequence number, okay, by 16. Well, what happens when you multiply by a power of 2? It shifts. Okay, it shifts it by 4 bits. Okay? So it's shifted the bits by 4 bits, and now if I right shift it by 8 minus 3, I capture the top 3 bits. In this case, 1, 1, 0, which is 6. Then I convert 6, it says I had a shift of 4. Okay? We doing okay? Okay? And just with 64 bits, it's a longer de Bruijn sequence. Okay? So this performance is limited by the fact you have to do a multiply and a table lookup, but it's generally fairly competitive for many machines that do not actually have a log base 2 of a power of 2. Okay, these days, machine instructions are getting, there are instructions that will do that in a single instruction for you. Okay, but if you don't happen to have one on your architecture or have, and need to do this fast, this is a reasonably fast way to do it, even with the table lookup and the thing. The other way of doing it, of course, would be to shift by 1, shift by 1, shift by 1 until you get the 1. And there are some other techniques as well that you can use. You can do divide and conquer in a binary way, where you do binary search for where the bit is by shifting and so forth and hone in. But the problem with those techniques, the binary search in particular, is what? If I try to binary search to find a bit, what's that going to be? Yeah, branching. You're going to have unpredictable branches. Okay, and each of those will cost you 16 cycles. And so with a 64-bit word, you've got 16 cycles times 6 bits that you're trying to decode, okay, times however many instructions it actually takes you. It adds up to a lot of cycles. Okay? But that can sometimes be an effective way of doing it as well. And there are other ways. You can look, byte by byte. There are a variety of other techniques. Anyway, but this is a cute one. Okay? Here's another one. Population count. Okay? Count up the number of 1 bits in a word. Okay? So here's one way of doing it. Okay? I start out r at 0, and I keep incrementing r. And what I do is I quit when x is 0. And what I do is I do that trick of x ANDing it with x minus 1, which does what? Eliminates the low order bit that's 1, the low order 1. So I basically go through and I just kick out one of the 1s, kick out another one of the 1s, kick out another one of the 1s, until I'm done. This has a branch in it, but in some sense it's a predictable branch because almost all the time you're going through the loop. Okay? However, it has a downside, which is that suppose you're given minus 1. Okay? Then you have to do 64 iterations of this loop before you can get your final answer. Okay? And so that's a lot of iterations to do. Okay? So here's, here's what's going on near the loop. Here's x minus 1. Okay? And now if I AND them, it's very similar to the other trick that I taught you. If you AND them, notice you have the same number you started with, except it's missing the 1 low order bit. Okay? So this is fast if the population count is small. If you know there's only a couple of bits on in the word, then this can be a pretty effective technique. But in the worst case, it's going to be proportional to the number of bits in the word because you're only getting rid of 1 bit at a time. But it's better in some sense than looking 1 bit at a time because you have the off chance that the number of 1 bits will be sparse. Okay, whereas if you just looked at the low order bit and then the next bit and the next bit and the next bit, that would be, definitely take you worst case every single time. Okay, here's another way to do it. Okay, it's a table lookup. So you have to pay, but if you're doing this a lot, maybe all of this is in L1, so the table lookup only costs you 4 cycles if it's in L1 cache. Okay? So what is this sequence? This tells for any given byte, so there's 256 values, how many 1s are in the world. So 0 has 0 1 bits. 1 has 1 1 bit. 2 has 1 1 bit. 3 has 2 1 bits. 4 has 1 1 bit. 5 has 2. 6 has 2. 7 has 3. 8 has 1, etc. So that's this table. I didn't fill out the rest of the table. And now what you're doing in this loop is you're basically taking a look at the value of x. You're right-shifting it, and then you're indexing, masking with the low-order byte. So you mask the low-order byte. You add that to the count by doing a lookup, okay, which hopefully only takes you 4 cycles if the table is in L1. Okay, and just run around this loop until you've got no more things in your word. Okay, so how many are in byte 1, how many are in byte 2, how many in byte 3, and so forth. Okay? So the performance is, for things that use table lookup, you have to be careful because you really, if you have a great big table, why not look up, 2 bytes at a time? Okay, well, 2 bytes is 65,000 entries. Okay? So why not look up 4 bytes at a time? So 4 bytes is 4 billion entries. And at that point, you're going out to memory and starting to consume a lot of space. So here's some common numbers. These are sort of approximate. But generally, if you're doing operations on registers, 1 cycles and plus, you can issue 6 per core per cycle. Okay? If it's an L1 cache, it's going to cost you around 4 cycles. L2 cache about 10, L3 about 50, and DRAM about 150 to 200 cycles. Okay? When you access these, you get, in fact, generally for all of these, you tend to get a 64-byte cache line. Okay? So you're getting more than one. But if what you're doing is random access in a table, It doesn't help that all those other bytes are coming in. Okay? Okay. Population count 3, using parallel divide and conquer. This is the clever one. Okay? Here's the code. Okay? It's all register operations, basically. Okay? So it's creating some masks. So let's just take a look at what does this first instruction do? Okay? It's taking -1, it's shifting it left 32 bits. So that gives all ones in the high order half of the word and all zeros in the low order half, and then it's XORing it with -1, with all -1s. So that gives you a mask of ones in the low order half of the word. Yeah, question?
-1 right shifted, isn't there a type of right shift?
Yeah, you can do that. I was trying to be consistent here. And in fact, for these first two operations, there are actually more clever ways of doing this that take a fewer operations.
Well, I mean, isn't there a right shift operator that fills in zeros in the top level?
Yeah, so there's logical versus arithmetic right shift. Yep. That's right. But then I wouldn't have the pattern that I'm setting up here. Okay? So yes, in fact, if you want to play with it yourself, you can optimize these first two statements. They don't need to be as complicated as this one. Okay? But basically what you're doing at every step is you're shifting it over half the word, XORing it, and then the second one is you get a block of 16 bits of zeros, 16 ones, 16 zeros, 16 ones. The next one you get a block of 8 zeros, 8 ones, 8 zeros, 8 ones. And so basically you're generating masks for that. So by the time you get down to the last one, you're having every other bit is 0. Okay? You're alternating zeros and ones. And then basically, well, let me not go through the code here. Let me show you with an example. The main thing to observe is that it takes log n time, where n is the word length, to do this. Okay? So here's population count on 32 bits. Okay, same kind of thing. So here's the idea. Okay? We extract every other bit, okay, for the two words. So you saw how I extracted that, right? So we extract. So I can do that with a mask and a shift, okay? And then I add them together, okay? So just so we can see what's being added here. Okay, and when I add them together, the largest value I'm going to have in any one of these things is what? 2. And that, fortunately, fits in 2 bits. Okay? So we can get off the ground. Okay? So now every 2 bits has the sum of the 2 bits that were there. The bits that I'm not showing are all zeros. Okay, because it's done on 64-bit words. The bits I'm showing are all zeros. Okay? So now what do we do? Okay, we shift now, we mask and shift, and take off every 2 pairs of bits, and then add them together. Okay, so now this guy is saying there's 4 bits that were originally in the word that began. Okay, this one says there are 2 bits in that range, 1 bit, 1 bit, 2 bits, 3 bits, 2 bits, 2 bits. Okay, there are ones. So do it again. Okay, add it together. Okay, and we just keep going. And then finally we add them all together. Okay, it says there's 17 ones in the word, which there were. I should have probably left the word up there or something so we could verify that. But yeah, there's 17 ones. So everybody see it's parallel divide and conquer, right? Because you're adding many words, many sub-pieces of the word of product. And the key thing is to make it so that no carries are propagating out of their range. But the numbers are just getting smaller and smaller. When you're done, you're only going to have 6 bits here that are significant anyway. All these will be zeros. Okay. Is that cool? Okay? So there's a 17, yep. Okay. Here's a problem for which bit representations are a lot of fun. Okay? Last year we gave this as a problem to students. This year we're giving you a different problem. So that lets me lecture on it. Okay? Okay, so many people are probably familiar with this problem. It's an old chestnut. It's basically the queen's problem is to place n queens on an n by n chessboard so that no queen attacks another. So there are no two queens in any row, column, or diagonal. Okay, so queens kind of move like this. Okay, it's got to be clear. If I did that around any one of these guys, they wouldn't hit anybody else. In fact, this arrangement here is, I think, one of the few symmetric ones. Maybe it's the only symmetric one. It's radially symmetric. Most of them are sort of more scattered. Okay? So the question is, how do you find such a thing, or count the number of solutions is another popular one, et cetera. So the strategy that, a popular strategy for this is called backtracking search. Okay? And we're going to have in your homework a different backtracking search. Okay? And the idea is you just simply try to place the queens row by row. Okay? So for example, we start out with the first row, row 0, and we place a queen. Then we go to the next row. Then we try to see if a queen works on that square. Nope. Nope. Ah, yes, it works there. Now we can go on to the next row. Okay? So this is making progress. We're placing queens. We're going to more rows. We're going to get to the end of the rows, right? So we keep. Aha! Yep, we found it. Okay? And we keep going. This is easy. Okay? Found it right after 2 there. That's pretty good. Okay? Found it there. Okay. Look, we're making great progress. Okay, doesn't go there, doesn't go there, doesn't go there, doesn't go there. Oops, doesn't go anywhere. So what do? We backtrack. Okay? We say, gee, if it didn't fit in any of those, then it had nothing to do with the placement there. It's the fault of the guy who came before me. So that position is not a valid position, at least with that prefix. So we continue with him. Oops. Aha, we found another place for him. Okay? So then we try this one. Oops, this doesn't look good. Aha, got to backtrack. Whoops, that's the last one in the row. Got to backtrack again. Okay, so try that means that guy can't go there. Okay. Ah, found a place. Now we get to go forward. Hooray! Okay, and you keep going on. So you backtrack, etc., until you finally find a placement for them. Okay. So the backtracking search is pretty interesting, but the question is, how do you represent it so that it can go really fast? Okay? So here's some ideas. The first idea you might come up with is to use an array of n squared bytes, where you put a value in the byte if there's a queen there. Okay, you should, at this point, figure out that, gee, all I have to know is whether a queen is there or not, so why should I keep a byte? Why not just keep a bit? That'll be smaller and have a smaller representation. So let's keep n squared bits. Okay? Well, let's see. If I'm only putting a queen in one place in every row, I never have to have more than one bit set in any row. So why not just say the column number in the row that I'm in? So rather than using an array of n bits for every row, let me just use an index of a byte to say how many to say which row that one queen is in, because there can't be any other queens in that row in a legal configuration. Okay? So that's actually more clever, and that's the way most people code it. But we're going to look at a solution that was originally due to Edsger Dijkstra of using 3 bit vectors to represent the board. Okay? And the idea is we want to make things go, we're going to use 3 bit vectors that are relatively small. Okay? So it turns out the n queens is an exponential search problem, and so you really can't run n queens on 128 by 128 board. Okay, not if you can run that if you are interested in one solution. You can't count up how many solutions. And if you go to Wikipedia and look at n queens, they'll tell you what all the latest records are for who has computed how many solutions there are on an n by n board for n up to some rather small number. Okay, so it's a way to make way to get your name on the web, which, as you know, is very difficult to do. Okay, so let's see this 3 bit vector trick. So the idea of the bit vector trick is that for any partial placement, rather than representing where the queens are on the board, what I really care about is which columns have been knocked out, okay, for the columns. So therefore, what I'll do is I'll store a 1 if there's a queen in that column, and a 0 if I don't have a queen in that column. Okay? So the point is I can keep the whole representation of the column mask, okay, in a word that just tells me whether I have 1s or 0s in a column. Now, how do I know whether it's safe to place a queen in a given column? What's that? Can check. How do I know, if I try to place a queen, say, here, how do I know whether that's okay or not? Suppose that my program wants to try to put a queen in this space. Okay, it can't because there's something here. That's just some operations on words, okay, which we'll see here. So placing a queen in column C is not safe if this down word here, when I AND it with 1 shifted left by the number of columns so that I have the position of the queen in the column, if that's non-zero, because it means somebody else is in that column. If it's in a new column, when I do the AND, I'll get all zeros. Everybody follow that? So testing columnness, whether it's safe to put it in a given column, from the column attack, we can do that really, really efficiently, right? That's all, these are all going to be in registers. Okay? No memory operations, no table lookups, no L1 caches, all right in registers. Okay? Okay, well, what do we do about the diagonals? Okay? So for the diagonals, we can also use a bit vector representation for each diagonal. Okay, where I look to see if there's a number along this diagonal. Okay, and if there is a queen, then it's a 1. And if there isn't a queen on a diagonal, it's 0. There are more diagonals than there are columns, right? So I have a longer bit vector representation. I have to represent that. Okay, but I can still do that in one computer word for things of different size, or even for things that are pretty good size, 2 computer words would be certainly ample. Okay? So now how do I tell whether or not a queen placed on a given square can legally be placed there? Okay, so it turns out it's not safe to place it if when I take my right array and I take n minus r plus c and left shift it by that amount, and that's non-zero. Okay, so here I'm indexing rows and columns from the upper left-hand corner. Okay, and so basically you're trying to say is for a given square, notice that if I increase the row, that's this way, I'm decreasing, I get to the same, so what do I want to say here? If I'm increasing the row, I'm decreasing the diagonal that I'm on. But if I'm increasing the column, I'm increasing the diagonal I'm on, right? So that's why it's basically a difference here. And then you just normalize it, and with essentially a very, very few operations, I can tell whether there's a conflict in a column. Of course, for both this and the other one, if I need to set it now, that's pretty simple also. I just take this and OR it with right. Okay, if my test is good, then I just take this, OR it with right, and now that's my new right. Okay? And left is similar. Okay? So once again, we have these guys going this way. Placing a queen in row R and column C is not safe if, and now I just look at row plus column, because these diagonals increase with both row and column. Okay, you're increasing the diagonal for both row and column. And so I'm not going to go through all the details of the code, but you can see that with this representation, literally the inner loop of your program, which is testing whether queens fit on boards and then setting them if they do, you can do with just 3 words and a few operations. Question?
Can you mask the 3 bits together and check if one position is taken up? You'd have to do some creative stuff with lining up the row and column vectors with the diagonals, but
So typically here you're looking at both row and column. So you're adding them, whereas on the previous one you were subtracting. And then the first one you didn't even care about what the column was. So I'm not sure that I would know how to combine those. It's conceivable you could do it.
I guess I was thinking more for the row vector and the column vector. You can add the 2 together and find specific positions that are free.
Yeah, so you can also do a generation that says here are the ones that are free, and then use things like the least significant bit trick to pull out what is the positions I should bother to check. Okay? So that's exactly, so here I can test if it's safe, but I can also generate, using similar tricks, which is what you're saying, generate all of the bit positions on a given row where it would be safe to put a queen. Yep. Yep. Good. So fast programs use this technique. Okay? So you see that there's a lot of cleverness in these kinds of techniques. Okay. So there are a whole bunch of other bit hacking techniques. One really good resource for it is this web page. And of course, I'll put this up on the called Bit Twiddling Hacks, where he's compiled. There's a lot of people who have worked on different bit twiddling hacks, and he's done a very good job of compiling what he thinks are the best code sequences for a whole bunch of things, including things like reversing the bits in a word. If you think about it, that could be kind of tricky. Actually turns out to be relevant to your homework as well. Okay? So on your homework, okay, so lab 1 will be, it's posted, I gather, right? It'll be posted shortly, okay? We have you trying to take advantage of some of these bit tricks, okay, in a couple of warm-up exercises and then a backtracking search algorithm, okay? And so I think you'll find it's a lot of fun. You'll learn a lot about all the kinds of tricks that you can do to make stuff go fast by using register operations locally and using good representations for your storage. Yes, also announcement, tonight at 7 o'clock, okay, in 32144, there is a primer on C. So if you want to brush up on your C or you want to learn C, this is a good time to go. There's a lot of good nuggets of wisdom coming out for C. Okay, thanks very much. See you Thursday.